All right, yes. 2 to the power of 0 is 1. And then you guys know your powers of 2, like 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. We don't need to do the calculator work for those. And then using our either review for the 2D people or the new stuff for the people that took grade 10 applied, you guys know 2 to the power of minus 1 is just the reciprocal of 2. And 2 to the power of minus 2 is just the reciprocal of 4. And then 2 to the power of minus 3 is just the reciprocal of 8, 1 over 8. So at this stage in the unit, we don't need to have our calculators out for that. Let's plot these points and see what we get. We're going to start talking about properties of the graph we get. So do the best you can with these smaller values. Those are pretty close to 0. But 1 over 8 is not 0. It's like 0.125. So teeny tiny bit above the x-axis there. And then 0.25 is like a quarter of a tick. I'm doing my best. I'm 43 and my fine motor skills are deteriorating. But I'm going to do my best. 0, 1, 1, 2, 2, 4, and 3, 8. Everything fits on there pretty nice. And what we get is something that looks like this. So it might take me a couple of tries. We get a graph that's pretty flat and slowly increasing, but then it starts increasing faster and faster and faster, and it's just going to keep shooting up at a faster and faster rate. 16, 32, 64. It's just going to keep swooping up like that. But to the left, these, because of our negative exponents, these fractions are never going to get to 0, but they're going to become teeny tiny little fractions, and our graph will level off, but not quite approach 0. With this graph, let's state some properties. Some of these will be new to you guys, but some of them aren't. So you guys can see this graph has a y-intercept of 0, 1. We pass through the y-axis at the point 0, 1. Let's jot that down. Now, as you move to the right, is this graph increasing in value or is it decreasing? Like, what's happening to the y values? As you move to the right and the x values increase, what happens to the y values? They increase too, right? We can see this graph shooting up, getting bigger and bigger. So we'll just kind of check the increasing there. It's increasing. A new property for you guys is called an asymptote. So you will note that this graph, to the right, it shoots off forever and ever on that. But to the left, it flattens out and flattens out and flattens out. And no matter how far left you go, no matter what negative number you pick, you're never going to get 0. It's always going to be some teeny tiny little fraction, but it's never going to be 0. So our graph levels out and approaches this horizontal line. That is called an asymptote. And this graph has an asymptote at y equals 0. So asymptote is, maybe I can just tuck this underneath here. It'd be a good idea for you guys. An asymptote is a, let's just say, an imaginary line. Our graph approaches. Our graph approaches. For those of you guys who take grade 12 functions next year, you'll kind of formalize that a little bit more. But for our purposes, it's fine. Okay, so this exponential function has a y-intercept of 0, 1. This one's increasing. Some new tech for you guys. It approaches this imaginary line, y equals 0. And then let's look at the domain and range. Anytime we sketch a new function, we look at its domain and range. What kind of x values can we plug into our function 2 to the power of x? Is there any kind of number, an x value, that you can plug in to break this function so it gives you an error message? And the answer is no. You guys have learned why. Not only can you plug in positive whole numbers like you're in grade school, but you can plug in 0, you can plug in negatives, you can plug in fractions, you can plug anything in you want as the power of 2, and it's going to spit out a y value. So the domain of this exponential function is x can be any real number. The way we say that is our curly Q brackets. X can be any real number. And on the graph, you can see that's true because the graph keeps going forever to the right. It's going to keep getting really big, but it keeps moving right, and then the graph keeps moving left as well. But the range, we don't, on the y values of this graph, 2 to the power of x doesn't touch all the y values. You guys can see on the graph the y values it hits. The y values hit all these positive numbers, but this graph never touches 0, and of course it can't be negative if it never touches 0. So the range for this function, we say this: y can be any real number such that y is greater than 0. Just greater than. This graph will never touch 0 because it approaches 0, never touches it. So this is our first exponential function of the day. Towards the end of the day, we want to be able to graph any function, exponential function, that looks like this. The last piece I want to fill in here, for this function here, the base was 2. Can you guys pop that in there? The base was 2. And we didn't scale that by any number. We didn't multiply by a number out front. And so this a value we assume is equal to 1. We didn't multiply it by anything. If you feel more comfortable, you can write your function like this: 1 times 2 to the power of x. The base was 2, and we didn't multiply it by anything different than that. So what we're going to do is we're going to repeat this drill and see what kind of properties stay the same, what kind of properties change as we change up A and B. So this should go by a little bit more quicker now that we've talked about all these properties. The last thing I want to note for making this table of values, do you guys see what's changing every time you go up a y value? Every time you increase the x by 1, we're doubling the y values, right? So I'm going to add one more thing on there, maybe in a different color. Multiplied by 2, multiplied by 2, multiplied by 2. I might just stop here, and you guys can see that's the pattern. That'll help us make these graphs a lot easier. So as we kind of move along and do a few more, we want to start thinking about how could I just make a sketch of that function without having to do a table of values. All right, here we go. Let's do a second one. Let's do f of x equals 0.5 to the power of x. So here, if you want to rewrite this, you could write it as 1 times 0.5 to the power of x. So what will this graph look like if our base is 0.5 and what we're multiplying by out front is equal to 1? And let's just make a table of values together. For this one, I don't mind if you guys use a calculator. We don't actually need one. We can do a couple together. Like this one, everybody should just automatically 0.5 to the power of 0. You shouldn't have to think about it. It's equal to 1. Well, you know what? Why don't you guys take your calculators? Why don't you just grind out a few of these powers and then see what you get? I'll maybe do my attendance while you guys just hammer those out. Make sure to stop the recording. All right, and we're back. I'm going to play some catch up here. So you can just slam these out. 0.5 to the power of -3. You guys should have got 8, right? You guys get 8? You probably, after you do a couple, you see the pattern. 0.5 to the power of -2 is equal to 4. 0.5 to the power of -1 is equal to 2. You guys see the pattern for this one? 8, 4, 2, 1. You're just dividing by 2, or in other words, you're multiplying by 0.5. Means the same thing. So, feel free to put those in your calculator, or you can just keep dividing by 2 all the way down. 0.5, 0.25, 0.125. And let's plot these points and see what kind of graph shakes out. regret writing my 0.5 so big because I got a point there I want to plot. I'll just fix that up. I have that luxury. 0.5, 0.5, 0.5. And so as we plot these points, let's think about what's different about this one compared to the previous one. Plot those decimal values the best you can. That wasn't so bad. Okay, that looks okay. All right, here's the graph. Can you guys check off all these properties? What's the y-intercept? Is it increasing or decreasing? Is there a line we're approaching? What's the domain and range? What's the same? What's different? I'll give you guys a minute or so to get a head start on that. What's the same? What's different? Let's fill in these properties. Again, what we'd like to get to a point where we could just sketch these graphs by hand without having to do a big table of values. All right, I can't wait any longer. Y-intercept is 0, 1 again. Our asymptote for this one flattens off at y equals 0 as well. But this time it goes to the right. As we go to the right, this levels off and approaches that horizontal line y equals 0. The domain is the same as the previous one. The range is the same as well. The only difference here is that this graph, as you move to the right, the y values are getting smaller and smaller. This one's decreasing. Hopefully, you're making some connections between the numbers in the equation and what's happening with the graph. Let's do one more. I think it'll become even more clear after this one. So now we're going to graph the function 4 times 0.5 to the power of x. So here, we've got that same base as before, 0.5. Let's see what stays the same. Let's see what changes when our a value is 4. Now, you don't really need to redo all these powers on your calculator. Just take the previous values and just multiply them all by 4. So we had 8, 4, 2, 1, 0.5, 0.25, 0.125. Just multiply them all by 4. We don't really need to do a lot of crazy work for this one. So that would be 32. And then 4 times 4 is 16. 2 times 4 is 8. You guys seeing the pattern for this one as well? It's kind of the same pattern as the last one, right? Our y values, we keep dividing by 2 or multiplying by 0.5. Interesting. The equation has 0.5 to the power of x, and our y values keep having or being multiplied by 0.5 every time. And I think we get down to 0.5 if we follow that pattern or just multiply all our y values by 4. Let's plot the points we can. Let's see how the shape of the graph is different. What's the same, what's different? So minus 332 can't fit. Minus 216 can't fit. Minus 1, 8 we can fit. 0, 4, 1, 2, 2, 1, 3, 0.5. And you know what? If you wanted to, it'd be 4.25. You can kind of continue on. But look, it's kind of a similar shape, right? Swooping down. I can do better. Swooping down. If I tilt my head sideways, it'll make it work. Okay. Yeah, it's okay. Do you guys agree? Same basic shape as the previous one? It's kind of swooping down and leveling off to y equals 0. Compared to the previous one, 0.5 to the power of x, what's the one property here that changed? Anybody spot it? What's the one property that changed? Right? The y-intercept for this one is 0, 4. I wonder where that could appear in our equation. So maybe that we could predict where the y-intercept is in the future. 4 times 0.5 to the power of x. The y-intercept was 4, and our y values were multiplied by 0.5 every time. They have. Let's jot in these properties here. This y-intercept was 0, 4. And then everything else was the same as the previous one. It was decreasing. We flatten out at y equals 0. The domain is x can be any real number. And the range, same thing. The y values are always above 0. Interesting. Now for this last one, I wonder if you guys could make some predictions about what this graph would look like before we even start. When our a value is 2 and our base is 3. Do you guys think you could use the 3 previous to predict the y-intercept and whether it's increasing or decreasing and what the asymptote, domain, and range would be? I would challenge you to maybe fill in these properties first. And then we'll, of course, do the table values together. But I'm going to wait a minute or 90 seconds. I would strongly encourage you to maybe try to make some predictions. Some of these properties were the same no matter what. Some of these properties depended on A, some of these properties depended on B. So I'll wait a sec before we do the table of values. I will sit on my hands and enforce some wait time here. Hi, Claire. This one. All right, guys, I'm going to come along for the ride here with the table, and I'm just going to talk through filling out the table, and let's do what happens when we plug in x equals 0. Well, we're doing 3 to the power of 0, but then we're also multiplying that result by 2. 3 to the power of 0 is 1. 2 times 1 is 2, last time I checked. And maybe we could use mental math for the next one. 3 to the power of 1 is 3. Multiply it by 2. We get 6. 3 squared is 9. Multiply that by 2. We get 18. And hopefully you guys recognize the pattern after doing a few. Our base is 3. And what happens to our y values each time? We're multiplying by 3. We're multiplying by 3. So this last one will be whatever 3 times 18 is, 54. And if you work backwards, you can get the y values just by working backwards. And just instead of multiplying by 0.5, you can just work backwards and multiply by 2. Or, divide by 2. What am I doing? That's multiplying by 3. I got 0.5 on the brain. Disaster. Let's fix that up. Apologies if you're working in pen. Why are you working in pen in math class anyway? That's your fault. So we're multiplying by 3. That makes more sense. And then working backwards, what's the pattern? We just multiply by 3 every time. 2 divided by 3. You can use the decimal. I'm just going to write 2 over 3. 2 thirds divided by 3, you get 2 ninths. And then 2 ninths divided by 3, you get 2 over 27. A teeny tiny decimal number. Let's plot the points we can and then wrap this up, and then we'll summarize our findings. So what can we fit on here? 218. I changed the scale so we can fit, 2 18s over here. 218 we can fit on there. 1 6 we can fit on here. 0 2. And then 2 thirds is a bit more than half. And then at this point, we're just getting to be, the numbers are pretty small. But look, all these exponential functions have the same general shape. This one is increasing. And why was it increasing? Our base was 3. We're tripling the y values every time. What are the other properties? The y-intercept was 0, 2. Guys, look at the equation. 2 times 3 to the power of x. The y-intercept was 0, 2. Not a coincidence. It happened in the previous question. We approach y equals 0. This one's increasing. The domain and range, it's the same for all these graphs. X can be any real number. Y can be any real number such that y is greater than 0. Okay, so we've done 4. And at this point, I think that's plenty to be able to describe some general rules for these functions. So we can just start graphing them by hand. So let's summarize our findings here. All right. This little table will summarize everything we just did. So if you're thinking about what is the graph of an exponential function, a times b to the power of x look like? Well, it can look, there's 2 different ways it could look. The first is the graph could be increasing if the base is bigger than 1. Think about our graphs. When the base was 2, it was increasing. When the base was 3, it was increasing. When the base was 0.5, it was decreasing. And what does this look like? I'm just going to draw a little mini axis here, a little y-axis, a little x-axis. All of our increasing exponential functions swoop up like this. They all look the same. We'll leave it like that for now and might add some detail to that in a second. Not much more. And then if it's not increasing, our graphs are decreasing. And they're decreasing if, we got to be careful here. We can't just say the base is less than 1, because that would include all kinds of negative values for the base. And things get really, really weird when you have bases that are negative. So we're going to say it's decreasing if the base is between 0 and 1. And our fancy math way of saying that is that 0 is less than b is less than 1. And then we're going to make a little diagram here, a little summary. Those graphs all look like this. This is it. Our exponential functions can look one of 2 ways. Increasing if the base is bigger than 1, decreasing if the base is between 0 and 1. Hopefully that's what you took out of that little investigation. Now, other properties are the exact same, no matter what the values of a and b. Some of them depend, though. So let's just have a team talk. The y-intercept of any of these exponential functions we saw was simply whatever a was. The y-intercept is always 0a. So that's nice. You see an equation, you automatically know where you start at that value of a. And then the others are the same, no matter what. The asymptote, our graph always leveled off at 0, either left or right. The domain was x can be any real number. See, I'm pretending I'm one of you guys, fellow kids. Look at my crappy curly Q bracket, just a squiggle. I can do better. I got to set a good example for you guys. There's a nice curly Q bracket. X can be any real number. For you guys, a squiggle will suffice. For me, I'm going to do better. And the range, y can be any real number such that y is greater than 0. This is the meat and potatoes for today. You guys now know how to graph any exponential function that looks like this. This tells you the y-intercept, and this tells you if it's increasing or decreasing and at what rate. So let's just actually try a couple. Let's graph a couple exponential functions together. The rest will go by pretty quick today, guys. Oh, excuse me. Before we graph some, let's go in reverse. Here's a graph of an exponential function. So currently, to get this equation, you guys have 2 blanks to fill in for me. You've got the A value, and you've got the B value. Can you guys have a quick think? We just talked about what the A value gives you, so you should be able to find that. Our graph is increasing. Our base should be bigger than 1, but what should our base be? Well, if you guys look at the Y values and how they're changing, you should be able to figure out the base B. And maybe as a hint, I'll just like draw in some solid points here for you guys to see if you can figure out what the rule is. I'll wait 30 seconds, and then maybe somebody, one of you guys, can just tell me the equation of this exponential function. Can anybody do it? Maybe somebody hasn't helped out yet today. Give me the 2 blanks for us. 3 and 2, how'd you get 3? That's what the y-intercept is. And how'd you get 2? Doubling each time. 3 to 6, or 1.5 to 3 to 6. Very good. So filling in the blanks, I might just add a small note here. I'm just going to add doubling, which is where Forrest got that 2 from in the base. That is the graph of 3 times 2 to the power of x. Can you guys try this next one? 2 blanks to fill in here to build this exponential function. I'll add in some kind of key points here, just kind of some corner points, like so. Somebody different want to try this one? Gervin, you got this one? It is 2. Y-intercept is 2. Why do you think it's 2? Why do you think the base is 2? It's doubling if you go back this way. Yeah. Not -2. Yeah. So instead of it's multiplying by 2 this way means dividing by 2 this way. So dividing by 2 is like you're halving the values, 0.5. So you guys can maybe, if you want, you can add a little note here. You can say halving. I think that's how you spell halving. That means to divide in 2. You can say divide by 2. You can say multiply by 0.5. But that's the pattern. So you had it, Gervin, but when you're looking for the pattern, it's whatever the pattern is as you move to the right. That's good. All right, you guys take 1 more minute and try these next 2, and then I'll graph a couple with you. You need the y-intercept, and you need information about how the graph is increasing or decreasing to fill in our 2 blanks. I'll add in some key points for you guys. I'll get the practice distributed, and I'll get assignments to people that weren't here, and we'll take these 2 up, and we'll wrap up the lesson. You guys did great today. I quite enjoyed that. Got the note? And that's why you printed it off? I can help you with anything you have questions on. And then practice for you guys here yesterday. practice with you guys. And you need this. You're welcome. All right, let's wrap this up. Who's got the blanks for this one, the third one? Somebody who hasn't helped out yet today? Kemper. 0.5 is the y-intercept, and the y values are doubling every time. Perfect. And then somebody different for the last one. Gervin, Redemption, the Redemption Tour.
100 and 0.5.
0.5. The y-intercept is 100, and the y values are halving every time. So I'm just writing out a little the rule we're using. Halving, multiplying by 0.5, dividing by 2. All leads to a 0.5 in the brackets. All right. Let's finish this up. Let's go to the reverse. Let's sketch a couple. Okay. This will take no time at all. So we're going to sketch the function 1.5 times 2 to the power of x. Now you guys know what each thing means. The 1.5 is the y-intercept, and the 2 means we're going to be doubling. So the 1.5 gives you a place to start. So I'll start at 1.5. And then, if you need to use a calculator, that's fine. But every unit you move over, you're going to double that value. So if you want to, at the bottom, you can just write the sequence of numbers. When you double 1.5, you get 3. When you double 3, you get 6. When you double 6, you get 12. Let's just plot those values. 3, 6, 12. If you want to go to the left, you can. That'd be 0.75. And then my brain's shutting down. So I'm just going to sketch it as it is. But yeah, this is a nice sketch. It's got some detail. It's got some key points. It's got the right y-intercept. It's increasing. Bob's your uncle. All you need to graph an exponential function are those two things. All right, you guys have done really well. Let's wrap it up. The y-intercept here is 16. Oh, here's a new one. A base of 0.25. What do you guys think is going to happen here? It's between 0 and 1, so it'll be decreasing. But what kind of rule can we say, Forrest? You can say divide by 4, quartering, multiply by 0.25. I like divide by 4. If you want to put times by 0.25, same idea. But yeah, we know where to start, 16. And then keep dividing by 4. 16 goes to 4, goes to 1, goes to 0.25. And those are our next points. 16, 4, 1. We're getting pretty teeny tiny there. We're approaching the asymptote. All right. Hey, you guys did really well today. I think we hit the sweet spot for, I'm just going to end the video, for having some practice time.